Hello, everyone. Now let's have a quick review on the matrix notations that I think most of you learned in your linear algebra from your undergraduate program. So actually here we will use the OneNote to show you the typical matrix notations that will be used in finite element analysis here. So firstly, let's say how the matrix is introduced to the engineering field. Because as we know that the matrix is used to represent a simple system of simultaneous algebra equations. So matrix is used to represent a simple system of simultaneous algebraic equations. As you can see here, in order to make the presentation of a system of multiple simultaneous equations, we use matrix here. So, so in that case, typically the matrix are a rectangular matrix. Typically is a rectangular array of quantities in rows and columns. So in this case, its matrix is like a bracket, including a lot of numbers and quantities in rows and columns, very similar to your Excel spreadsheet. So in this course, we will use we will use in this course we will use the square or rectangular bracket to represent rectangular matrix. So this is for the matrix. So in the other case, we use another bracket to represent the column matrix. matrix. So those are the symbols you will see very frequently through this entire semester. So this is a representation of of the matrix right here. So let's look at some examples here. If we see we have some examples. So for example, if we have a system of equations, with two unknown variables. So if we have a system of equations with two unknown variables, yeah. So yes, I think everybody learned how to solve this type of problem. So we have two linear equations. So we have two unknown variables, x and y, and then we have two equations. And so this is a so here we have uh, the presentation of the two equations, right? Two equations. So if we express that in the matrix form, so we express. So if we express the two equations in the matrix form, we will have the following expressions. So we use the rectangular bracket to represent the constant numbers. So we have 5 and 3. Yeah. So the first column represent the coefficient for x, and the second column for the coefficient for y. And the second equation, we have the 8 and 7. And we use the different bracket to represent the unknown variables, x and y. And then we have the 10 and 20. So this is the equation expressed in the matrix form. So as you can see here, it is a very straightforward transformation from the two equations to the matrix form here. We just use a rectangular matrix to represent the constant coefficients for x and y, and we use the vector matrix to represent the unknown variables and all the constant number on the right side of the two equations. So this is the case we have the matrix form for a typical system of equations. So in our case, when we deal with the finite element model, right? So in our case, so for this course, we deal with the finite element model. In a finite element model, we use, so we deal with the forces. So that means that we can have the force matrix, depending on the number of forces. We have multiple forces. For example, for a two-dimensional, for a three-dimensional problem, we have the force F1x, F1y, F1z. For any given node or any given point in the 3D space, we need to consider the forces in three directions. So similarly, we have the F2x, F2y, and F2z. Until we consider the Fnx, Fny, and the F. Oops. And z. That makes sense, right? So we just list all the forces in three directions in the same matrix, in the column matrix here. So similarly for displacement, displacement of the displacements of all cases, and we have we use u for the x, v for the y, and w for the z. Because theoretically, we need to consider the displacement for any given point in the 3D space in three different directions, x, y, and z. Right? So we use u, v, and w for the displacement in the directions x, y, and z respectively here, until we consider all the points. So this is the case. This is actually in most cases, the forces and the displacements, the matrix, all these numbers, most of them are unknown to us. So the goal of the finite element method is to formulate equations to solve for the unknown forces or unknown displacements here. So typically there is a relationship between the force matrix and the displacement matrix here. So we have the stiffness matrix. So so the relationship between the force and the displacement can be expressed as a equation in the form of matrices, right? So the force matrix is equal to the stiffness matrix times the displacement matrix. So here the matrix K is called the stiffness matrix. So typically through this entire semester, we use the stiffness matrix in the level of element as a level of element to derive the stiffness matrix at the level of the entire system. Right? so that we need to deal with the elemental sleeve-list matrix. So we have the elemental, so we use the lowercase k. So depending on how many nodes are in one element, we can have the n times n size, the elemental matrix here. Yeah. It's pretty easy. So as you can see here, the quantities in the elemental sleeve-list matrix are expressed as the k with the subscript. So the first number in the subscript is the row number, and the second one is the column number. So similarly, based on the elemental sleeve-list matrix, we can have the global matrix. You can have the global sleeve-list matrix. So we use a uppercase key, since in this case it is very difficult to tell the difference between the lowercase key and the uppercase key in handwritings. So I use a cap there. So let's see, it's a K11, K22. So this is a global sleeve-list matrix. So actually, in most cases, the K of using finite element method to solve any problem is to derive the global sleeve-list matrix based on the elemental sleeve-list matrix. So actually, through this entire semester, we will spend quite a lot of time discussing on how we can start from the elemental sleeve-list matrix to the global sleeve-list matrix. So if we have the global sleeve-list matrix, we should be able to solve the unknown forces or unknown displacements by just solving linear or nonlinear equations there. So that's the computer can do on their best. So I think that's the review on the matrix notations. So in this video, we have already um, covered the most important information here. And after this video, I have already also assigned some quick practice for you to refresh yourself on the manipulation or operation of different types of matrices here. So hopefully that will help you to warm up yourself and to get used to the symbols and the notations that we will use very frequently through this entire semester. I think that's all for this topic. Thank you.